Visualizing, modeling, and forecasting crashes in Wake County, North Carolina. My name is Leon, and my partners with Cortland and Kelly. These are our research questions and goals that we have been answering throughout our research. Discovering the main factors that contribute to a crash, visualize and identify hotspots of crashes in Wake County, North Carolina, determine if the COVID-19 pandemic impacts the crash frequency, decide if we can forecast the number of crashes in Wake County, and lastly, examine conditions that help predict outcomes in terms of crash injuries. We utilize public data from the North Carolina Wake County Open Data Portal, which gets updated every month and has all the specifications for the car accident. In this database, we use two separate data sets, persons involved in crashes and reported crash locations. We combine the two data sets from January 1st of 2015 until May 31st of 2021 using the common variable key_crash, creating a data set with about 380,000 observations and 74 variables. Exploratory data analysis was the first step in the process of understanding and finding patterns within the crash dataset. We conducted univariate and bivariate explorations. Here are a few of our most important univariate exploration findings. After doing exploratory data analysis, we moved to identify hotspots of crashes in Wake County, North Carolina. To begin, we use multiple location variables within our dataset to create word clouds indicating where crashes occurred most often. In each word cloud, the larger the font size of the street, the higher of the crash frequency there was. After creating word clouds from the location variables, we moved to making heat maps. The capital of North Carolina, Raleigh, is heavily colored in a dark red in both maps, indicating that many crashes occur there. As we move further from the capital, the level of crashes tend to decrease.
This section's purpose is to determine the best model for predicting car crashes in Wake County using daily pandemic, daily non-pandemic, monthly pandemic, and monthly non-pandemic data. Initially, we began forecasting with the original daily pandemic data. Here we use the TBATS model, ARIMA model, and the combination of the two. The model with the smallest root mean square error is said to perform the best. Therefore, the TBATS model performs the best here. After handling the daily pandemic data, we decided to forecast with daily non-pandemic data to visualize the difference that the pandemic makes on forecasts. For the daily non-pandemic data, we use the same models, TBATS, ARIMA, and the combination of the two. And here we can see that the ARIMA model performs slightly better than the other two models. We conducted similar forecasts and analyses on the monthly pandemic and non-pandemic data as well. For the monthly pandemic data, we used ARIMA, TBATS, HoltWinters, and the combination, and we can see that the HoltWinters model performs the best out of the four. For the monthly non-pandemic data, we used the SARIMA, STLF, and the combination of the two models, and we can see that the combination of the two models performed the best out of all of them.
Our final step was to work on predictive modeling of crash outcomes. We had extremely unbalanced data with many more no injury responses than injury responses. To fix that, we tried a variety of balancing strategies, including oversampling, adding more injury responses, undersampling, removing no injury responses, and a combination of both over and undersampling. We then tested these all against each other for accuracy and found that our combination data set of over and undersampling that was the same size as our original data set proved to be the most accurate with a balanced accuracy of about 69%, which as you can see from this top table is much higher than the rest, except for the other combination model. Below that, we have the output of our fitted logistic regression model, which shows us estimates, standard errors, statistics, p-values, and the odds ratio. From here, we can identify some important variables, such as using no protection makes you about 2.5 times more likely to be injured in a crash. We also fitted random forest models to our data to try and see if we could find a predictive model that would give us better accuracy. We went through some of the same steps of creating data sets that were oversampled, undersampled, and a combination of both so that we could work with balanced data. Luckily, we were able to find that the combination data set that was a subset of the original unbalanced data set had a fitted random forest model with a balanced accuracy of about 85%, which is significantly higher than any of the logistic regression models and the rest of the random forest models. Once we identified this as the most accurate predictive model, we were able to look at the variable importance, which helps us see which variables are the most important for the accuracy of the predictions. And from the bar plot below, we can see that the two most important are unsurprisingly age and the most harmful event. We would like to briefly acknowledge the funding of this project by the NSF and the NSA. Thank you all so much for your time.